Atomic clocks are the most precise timekeepers in the world. These exquisite instruments use lasers to measure the vibrations of atoms, which oscillate at a constant frequency, like many microscopic pendulums swinging in sync. The best atomic clocks in the world keep time with such precision that, if they had been running since the beginning of the universe, they would only be off by about half a second today. Still, they could be even more precise. If atomic clocks could more accurately measure atomic vibrations, they would be sensitive enough to detect phenomena such as dark matter and gravitational waves. With better atomic clocks, scientists could also start to answer some mind-bending questions, such as what effect gravity might have on the passage of time and whether time itself changes as the universe ages. Now a new kind of atomic clock designed by MIT physicists may enable scientists explore such questions and possibly reveal new physics. The researchers report in the journal Nature that they have built an atomic clock that measures not a cloud of randomly oscillating atoms, as state-of-the-art designs measure now, but instead atoms that have been quantumly entangled. The atoms are correlated in a way that is impossible according to the laws of classical physics, and that allows the scientists to measure the atom's vibrations more accurately. The new setup can achieve the same precision 4 times faster than clocks without entanglement. Entanglement-enhanced optical atomic clocks will have the potential to reach a better precision in 1 second than current state-of-the-art optical clocks, says lead author Edwin Pedroso Penafiel, a postdoc in MIT's Research Laboratory of Electronics. If state-of-the-art atomic clocks were adapted to measure entangled atoms the way the MIT team's setup does, their timing would improve such that, over the entire age of the universe, the clocks would be less than 100 milliseconds off. The paper's other co-authors from MIT are Simone Colombo, Qi Xu, Albert Adiatulin, Zheyang Li, Enrique Mendez, Boris Braverman, Akio Kawasaki, Saisuke Akamatsu, Yanhong Seo, and Vladan Valetic, the Lester Wolf Professor of Physics. Time limit. Since humans began tracking the passage of time, they have done so using periodic phenomena, such as the motion of the Sun across the sky. Today, vibrations in atoms are the most stable periodic events that scientists can observe. Furthermore, one cesium atom will oscillate at exactly the same frequency as another cesium atom. To keep perfect time, clocks would ideally track the oscillations of a single atom. But at that scale, an atom is so small that it behaves according to the mysterious rules of quantum mechanics. When measured, it behaves like a flipped coin that only when averaged over many flips gives the correct probabilities. This limitation is what physicists refer to as the standard quantum limit. When you increase the number of atoms, the average given by all these atoms goes towards something that gives the correct value, says Colombo. This is why today's atomic clocks are designed to measure a gas composed of thousands of the same type of atom, in order to get an estimate of their average oscillations. A typical atomic clock does this by first using a system of lasers to corral a gas of ultracooled atoms into a trap formed by a laser. A second, very stable laser, with a frequency close to that of the atom's vibrations, is sent to probe the atomic oscillation and thereby keep track of time. And yet, the standard quantum limit is still at work, meaning there is still some uncertainty, even among thousands of atoms, regarding their exact individual frequencies. This is where Valetic and his group have shown that quantum entanglement may help. In general, quantum entanglement describes a non-classical physical state, in which atoms in a group show correlated measurement results, even though each individual atom behaves like the random toss of a coin. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.